Hello, everyone. Welcome to Physics Lab 10 for Physics 207 or Lab 11 if you're in Physics 206. And this lab is going to be on rotational equilibrium and torques. Okay, so to start this, I want to just give a couple of definitions first before I describe what torque is. And again, make sure you watch my video on how I collect the data. I also explain a little bit about what I'm going to talk about now in that video. So the first definition is something called center of gravity. And you can think of that as a location, right, or a point at which we can consider the entire weight of the object to be acting. So it's sort of like a mathematical average where you can consider the entire weight of the object to be acting. Now, typically, if you have some, solid object, then the center of gravity is going to be like three-dimensionally inside of that object, but it doesn't necessarily have to lie within the matter of the body. So for example, if you look at these next two pictures, if I have like, say, a boomerang or say a tire, then mathematically, you can show that the center of gravity is actually in the center of the tire, or in this case, it's outside of the boomerang, right? So it doesn't have to lie within the matter of the object. If it's something more solid, right, if this were a solid object, then it would be truly right in the center of the object itself, but it doesn't have to lie within the matter. All right, another definition, and this is going to sound very similar, and in effect it is, but there's a slight difference. So it's something called center of mass. So it's a point at which we can consider the entire mass of the object to be acting. And you might think, well, what's the difference? It sounds like, center of gravity, center of mass are exactly the same thing. Well, remember how we calculate the weight of an object. Remember, center of gravity depends on the weight of the object. Remember, weight is mass times g, right, times the acceleration due to gravity, which we assume is a constant around 9.8 meters per second squared. But it turns out in reality that g is not a constant. As you move away from the center of the Earth, g gets weaker, so that value decreases. So in effect, there really is a slight difference, especially if you have a very tall object that's at the surface of the Earth. There is a slight difference between the location of the center of mass and the location of center of gravity. Center of mass would just depend on the mass of the object. So if you had like a nice symmetrical uniform object, the center of mass would be right in the center of the object. But because the gravity is slightly stronger near the surface of the Earth and slightly weaker as you move away, then the weight, when you calculate the weight of those little bits of mass that are near the surface, those are going to be weighted more strongly than the little bits of mass that are near the top, that are further away from the surface. So that will shift down the center of gravity a little bit. Now, it's very subtle, right? You'd have to have an extremely tall object to have any sort of difference. So for all intents and purposes, the center of mass and center of gravity are really basically the same location. And for our purposes in this lab, we're going to consider them to be almost the same thing, right? Same exact location. So in reality, yeah, slight differences, but for our purposes, think of them as meaning, as being the same thing. Okay, torque. Torque is a quantity that sort of represents the ability of a force to cause a rotation. It depends on several things, and I'll explain this. I'll go over to the iPad in a second to explain this more carefully. It depends on the size of the force. It depends on the direction of the force, and it depends on the location of the axis of rotation relative to the line along which that force acts. Okay, so let me go to the iPad and explain this more carefully. Okay, so let's say we have this object. Let's draw an object here. Let's say it's free to rotate about this point right there. So this is what's called the axis of rotation. And now let's say I apply a force to this object maybe something like this. So this is my force F. Okay, it's a vector, right? Now, it turns out if you want to calculate the torque, which again represents sort of, it's a quantity that sort of represents the ability of that force to cause a rotation, then it depends on several things. Usually we denote torque, by the way, by the Greek letter tau. So this is torque here, torque. It depends on the magnitude of the force. So however many newtons, right, that force is, so the magnitude. And it also depends on a special length, which I'll call L here. And this is what we call the moment arm. And it turns out, at least for the two-dimensional case, that the torque could either be positive or negative. Okay, and I'll explain how you figure out that sign in a second, whether it's positive or negative. So positive or negative. All right, so what is this moment arm? Well, first of all, the line along which this force acts, so you can see sort of this force acts along this line. I'll dash it in here. This, some people call this the line of action of the force. Well, the moment arm is defined to be the perpendicular distance from the line of action of the force to the axis of rotation. So in this case, the moment arm would be this distance, the one that's perpendicular to the line of action of the force. So this would be L. And generally, L is, you know, when you're dealing with torque problems, it is probably the trickiest thing to find. You typically have to use trigonometry to figure out what L is because the object tends to be at some particular angle. However, in this lab, we're going to keep things pretty straightforward. And it turns out that our moment arms are always going to be nice horizontal distances. Okay, so there will be no trig needed for this particular lab. But in general, it's that distance which is perpendicular to the line of action of the force to the axis of rotation. Now, what about the positive and negative? Well, if I were to actually exert a force F on that object, right, and it's actually pinned, let's say there's some axle that it can rotate on, say at the axis of rotation, what would happen to this particular object? Well, it would rotate, and it would rotate clockwise, right? If you actually push on the object, it would rotate clockwise. So by definition, if an object, if a force tends to rotate an object clockwise, the torque is going to be negative. So clockwise is negative and counterclockwise is positive. So it's just a definition. Just have to remember that. Clockwise, negative, counterclockwise is positive. Now, there's one other thing. What if I had a force that when I applied it, I'll call it force A. Let's say the line of action goes right through the axis of rotation. What is the torque due to force A in this case? Well, remember, in general, the torque is going to be the force times the moment arm. So there's certainly some magnitude of the force, right? Maybe it's 100 newtons, whatever A is, whatever its magnitude is. But what is the moment arm in this case? Well, the moment arm is the perpendicular distance from that line of action to the axis of rotation, but that's zero, right? It's, since the line of action is going right through the axis of rotation, there is no distance between those two. So in this case, or in any case that you have a force that passes right through the axis of rotation, its torque is going to be zero. And by the way, the units for torque, since it's a force times a length, is Newton meters. So these units over here should be Newton meters. Okay, so the first thing that you guys will need to do is locate the center of mass of your particular meter stick. So I did this for you, right? So I had 1 meter stick. And how did I do that? I balanced it. So I balanced it by putting a knife edge on the meter stick and putting on a stand. I had to adjust the location of that knife edge until the meter stick balanced. And what I found was that the center of mass of the meter stick was 50.1 centimeters, or if I convert that to meters, it's 0.501 meters. So that's just the location where I had to put the knife edge so that the meter stick balanced, right? So that represented the center of mass of the meter stick. Okay, so part one, again, you want to make sure you watch the video on how I collected all this data, but part one was simply to find that center of mass, so I did that for you. Part two was to verify the second condition for equilibrium, right? Well, what is the second condition for equilibrium? Well, first of all, let me describe what rotational equilibrium is. Okay, so here's the definition for rotational equilibrium. If you have an object, right, a body, and it's either not rotating at all, so if it's static, or if it rotates, but it rotates with a constant angular speed, then the object is said to be in rotational equilibrium. Um, if its angular speed or rotational speed is increasing or decreasing, right? If it's changing somehow, then it would not be in rotational equilibrium. Then you'd have an angular acceleration. So in order for an object to be in rotational equilibrium, there has to be no angular acceleration. Now, the most common case, and the case that you will deal with in this lab, will be when the object is static. So if it's at rest, it's not moving at all, then we know it's in rotational equilibrium. Okay, and that's all the cases that we'll see in lab at least. Now, what's true if an object is in rotational equilibrium? Well, it turns out that if I calculate the sum of the torques, so this equation right here, the sum of the torques about any point that I choose for my axis of rotation, it has to sum to 0. So that's the condition for something to be in rotational equilibrium. The sum of the torques has to equal 0. And then this is called, it has a name, it's called the second condition for equilibrium. By the way, the first condition you may know from Newton's second law is that if the sum of the forces equals 0, then the object is not accelerating, right? So that would be the first condition for equilibrium. Okay, so let me go back. So we found the center of mass of our meter stick, right? So part two here, again, was to verify this second condition for equilibrium, the fact that the sum of the torque should equal 0. So let me show you how you should measure this, set this up, and do these particular calculations. The goal here is to calculate the sum of the torques given a particular situation. In this case, we have a 200-gram mass that hangs 20 centimeters to the left of the knife edge, right? And the knife edge is right at the center of mass of the meter stick. So in our case, it would be at 50.1. That's what a knife edge would be. So I'd have to hang this mass here at 30.1. And then I'm hanging 100 grams on the other side, on the right-hand side, at some location such that this meter stick is in rotational equilibrium. So it's not rotating anymore. It's completely balanced. Okay. So the goal is to figure out what this distance is. And if you think about it, right, if I give you the location that you had to hang the 100-gram mass and it turned out it was 90, right, 90.0 centimeters, then you could figure out this distance just by taking the difference, right, between that location and the location of the center of mass. And then make sure you convert to SI units, because ultimately we want that distance to be in meters. And it turns out that this distance is the moment arm, right? Because the force here is the weight, and we can calculate the weight, right? If we know the mass, we can convert the mass to kilograms. We can multiply by 9.8, right, mg, and that will give us the weight in newtons. So that's the force, and it acts downward. So the line of action of the force is going to be this vertical line. So the perpendicular distance from the line of action of the force to the axis of rotation, consider the axis of rotation right here, that's going to be this horizontal distance, which is what we're calling L2. All right, so let me go back to the iPad and show you how to set this up, because you'll have to do these torque calculations. Okay, so again, in our case, our center of mass was at 50.1 centimeters, right? And that's where I want to put my knife edge and my stand, and I'm considering the axis of rotation to be right at that point, at 50.1. And then 20 centimeters to the left of that, I'm going to hang a weight here. So remember, the mass itself was 200 grams, but we can convert that to kilograms. That's 0.2 kilograms. And then I'll call this M1. And that will give us a weight, W1, which is simply going to be M1G. And this distance, right, is 20 centimeters, or 0.2 meters. Ultimately, we want everything to be SI units. So where did I hang that when I did this experiment? I had to hang it at 30.1. Okay. Now on the other side, we're hanging another mass, right, at some location. I'll call this M2. It was 100 grams, which is 0.1 kilograms. So that means I can calculate the force, which is just the weight, by using, oops, this should be W2. Let me erase that. Is going to be M2G. And when I did this experiment out, I found that it balanced when it was hanging at 90. So the first thing you guys have to do is you have to calculate this distance, which we're calling L2, which is really just the moment arm, right? If this is the line of action of the force, then that perpendicular distance is going to be my moment arm. So L2 is just my moment arm. Right, so that's the first part of the question, to calculate that particular moment arm. Then you're asked to sum the torques about this rotation point, which is where the center of mass is, where that knife edge is. Okay, so think about what's going on here, right? I actually have 4 forces acting. I have the 2 obvious ones, right? W1, the weight pulling down, and it's really the tension and the strain that's in contact with the meter stick pulling down. I have weight 2 pulling down. I have a normal force, because the stand, right, is pushing back up on the knife edge, right? So it's ultimately pushing back up on a meter stick. And then, of course, the weight of the meter stick itself is a force, and that acts at the center of mass. So I'll draw it from the center here. I also have, I'll call it W, the weight of the meter stick itself. So I have 4 forces. So what I want to do now is I want to calculate the torque due to each of those forces, and I want to add up all the torques. Okay, so I have so basically what I'm doing is this, right? I'm doing the sum of the torques, and I want to see what I get. So this is what I mean by I'm trying to verify the second condition for equilibrium. So I have a torque due to weight 1. I have a torque due to weight 2. I have a torque due to the weight of the meter stick, and I have a torque due to the normal force, right? I have 4 forces, so 4 torques. And I want to see what I get. Now the question is, can we simplify any of those torques right out, right off the bat? Can we just eliminate any of those torques? Yes, because remember, the equation for torque is it's going to be, I'll write it over here. Remember, torque, to calculate it, it's plus or minus the force times the moment arm, right? We're going to need that to do each of these. Well, if you look at this picture, both the weight and the normal force, they're passing right through the axis of rotation, right? They're going right through the axis of rotation. So what's the what's the moment arm for both the weight and the normal force? It's 0, right? Neither of them has a moment arm, so therefore neither of them is going to contribute a torque about that point of rotation. So these two terms are 0 because their moment arms are 0, right? So there's no torque. So let's look at the rest of this. So torque due to W1. Well, the force is W1, that's just the weight. So I have, in this case, it would be M1, which is 0.2 times G, right, 9.8. So that's my force, right? That's the weight, times the moment arm. Well, what is the moment arm in this case? Well, it's this distance, right? That perpendicular distance. And by design, we set that up to be 0.2. So this is 0.2 meters. So that's my F is the weight times L. And then the only other thing I have to figure out is whether it's positive or negative, right? So imagine that W1 is the only force acting. How would it rotate the meter stick about the point of rotation? Would it cause it to rotate clockwise or counterclockwise? So if you imagine pulling down on W1, how is the meter stick going to rotate? It's going to rotate counterclockwise, right? So therefore, by definition, this is going to be positive torque. Then the other weight, or the other force we have is weight 2. So I want to compute the torque, so I need the force, which is the weight. So that was 0.1 times 9.8. And then what is the moment arm? Well, that's what you guys are figuring out. That's going to be your L2. So once you have that in meters, you want to plug that in. Okay, so the first question is to figure out L2. Well, it's just a difference, right? It's 90 minus 50.1, and then make sure you convert that to meters. So then you can plug that in. Now, is the torque due to W2 positive or negative? Well, imagine that W2 is the only force acting. How would it rotate the meter stick? Well, it would rotate it, let's see, clockwise, right? If you were to pull down on W2, the meter stick would rotate clockwise around the point of rotation. Therefore, this is going to be negative. Okay, so you're going to plug in your L2, you're going to do your calculation, and you're going to see what you get. And in theory, what should you get? If everything were perfect. Now, there could be some error here, right? So this may not be exactly what theoretically it should be, but in theory, what should it be? Pretty much 0, right? Because remember, the sum of the torques should equal 0 if the object, in this case, our meter stick, is in rotational equilibrium, which it is in this case, right? It's static. We set it up so that it's balanced, so it's static. Okay, the next part of the experiment, you're going to basically do this again, but now you're going to put a 50-gram mass 30 centimeters to the left and balance it by 100 grams at some distance to the right. And again, I did that experiment for you. You will see it in the video. And I found that when I placed 100 grams at 65.0 centimeters, it balanced. So again, I'm going to ask you guys to calculate L2, so that moment arm. Then you're going to calculate the sum of the torques about the knife edge. So just like I did here, right? Show that equation. And then assuming that there were no errors, what should that equal? What should the sum of the torques equal? Well, it should be the same as before, right? Okay, the next part. So part 3. So in this part of the experiment, let's bring this up. We're now going to use the second condition for equilibrium to predict the mass of the meter stick, okay? So here's my meter stick. Remember, again, our center of mass was at 50.1 when I did this out. Now I'm going to set this up so that the knife edge is 20 centimeters to the left of the center of mass. So this is 0.2 meters, right, or 20 centimeters. And I'm going to assume that the axis of rotation is right at the knife edge, right at the stand. So basically what I did was I put this knife edge at 30.1, right? Then I hung 200 grams. So I'll call this M1, 200 grams, which is the same as 0.2 kilograms. And that is going to give me a force, which is the weight. How do I get that? I just multiply M1 times G. So 0.2 times 9.8 is the actual force, right? And it turns out that this balances. So I had to place that at some location such that the entire meter stick was balanced. So it's in rotational equilibrium. And it turned out that it balanced when this location was 10.9. So when I put it at 10.9 centimeters, it balanced. Okay, so what I want you to do is I want you to figure out what this moment arm is, which in this case I'm going to call L. And then I want you to calculate the sum of the torques, set it equal to 0, and then use that to figure out the mass of the meter stick. So in this case, there's actually 3 forces acting, right? I have the obvious one, the weight that's pulling down, right, W1. I have the normal force here that's pushing up, right, on the stand. And then I have another weight, which is now the weight of the meter stick itself. So where do I draw that vector? Well, I would draw it acting at the center of mass. So I'll just call this W. And this is equal to the mass of the meter stick, which we don't know. We're trying to predict that, times G. Right, so I have 3 forces acting. So when I calculate my sum of the torques instead of equal to 0, I want to include 3 torques. I have 3 forces, I want 3 torques, okay? So to do that, make a little room here, right? So now I'm gonna apply the fact that the sum of the torques should equal 0. I'm gonna apply that equation to solve for the mass of the meter stick, right? I wanna predict the mass of the meter stick. Okay, so I have a torque due to W1, weight 1. I have a torque due to the weight of the meter stick. I have a torque due to the normal force, and that's all going to equal 0, right, when I sum them up. Now, can I eliminate any of these torques right off the bat? Well, again, if you think about it, right, remember torque is force times moment arm. Because the normal force, it passes right through the axis of rotation, right? It's going right through where we're considering our axis of rotation to be. Therefore, its moment arm is 0. So the torque due to the normal force is going to be 0 because there is no moment arm there, okay? So we just have a torque due to W1 and a torque due to the weight of the meter stick. So what's the torque due to W1? Well, it's going to be the force, which is the weight of the hanging at W1. So that would be 0.2 times 9.8, right? That's the weight, which is the force, times the moment arm. Well, what's the moment arm? Well, that's something you guys had to figure out. That's going to be your L, right? Make sure that this is in meters, right? So you can find the difference, find it in centimeters first, and then convert centimeters to meters. Make sure it's ultimately in meters. Now, is the torque due to W1 positive or negative? So if you imagine that weight 1 is the only force acting, how would it rotate the meter stick? Would it rotate it clockwise or counterclockwise? Well, in this case, think of like pulling down, right? If you're pulling down on it, it's going to rotate it. I think I'm backwards in the video. It's hard to see. Yeah, if I pull down on it, it's going to rotate it counterclockwise, right? So that's going to be a positive torque. So it's plus. And then for the weight of the meter stick, well, the force is the weight. We don't know M, so I'm just going to leave this as M. G is just 9.8, right? And then what is the moment arm? Well, by design, it's this distance which we set to be 0.2 meters. So this is just 0.2. And is that torque positive or negative? Well, again, if I have my meter stick here, and now I'm pulling down on this side, right? It's going to, so imagine that you're pulling down on W, it's going to rotate it clockwise. Again, it's hard for me to figure out which way I'm going because it's sort of reversed in the video there. So it's going to rotate it clockwise, which by definition is negative. Okay, and that's got to equal 0. All right, so remember, you guys are going to know what L is, right? You have to compute L, so you can plug in L. Oops. Again, make sure it's in meters. And then once you have that, your only unknown for that equation will be M, so you can solve for M. It turns out you're going to find that it's just going to be equal to L, but that's just by luck, depending, you know, based on how our numbers worked out, like the 9.8 and 0.2 are going to cancel. But like walk through that, go through that and solve that equation for M. That's going to be the predicted mass of your meter stick. Okay, so solving for M will give you the predicted mass of the meter stick. All right, let me go back to the handout. Okay, so again, let me just go over this to make sure we didn't miss anything. So question 1, remember this was the part where you hung 200 grams, 20 centimeters to the left of the axis of rotation, and then 100 grams at some distance, L2 to the right. So question 1 was, given that the meter stick balanced when 100 grams was placed at 90.0 centimeters, so that's where the location at which it balanced, calculate the moment arm L2. So find that first. And again, it's just going to be the difference, right? Then calculate the sum of the torques about the knife edge. Make sure you show me this calculation. So given what I did on the iPad, make sure it's something very similar to that. Question 3, assuming there were no error in placing the mass, reading the location on the meter stick, etc., what should the answer be to question 2? So in theory, what should the sum of the torques equal if it's in rotational equilibrium? Then you're performing the experiment again. So now I place 30 grams at 30 centimeters to the left and 100 grams at some distance to the right. And in this case, I found that everything was balanced when the 100 grams was placed at 65 centimeters. So I want you to calculate L2, the moment arm again, right, in meters. And then calculate the sum of the torques about the knife edge, right, see what you get. And then assuming there was no errors, what should you get for the sum of the torques? Then the part that I just finished discussing, experiment part 3, this was where we had 200 grams. It was at a distance L away from the axis of rotation, right from the knife edge. And the knife edge itself, we placed 20 centimeters from the center of mass of the meter stick. Okay, so it was set up like that. And then what we wanted to do was place this 200 grams at some location so that everything balanced. And then we want to use the second condition for equilibrium to predict the mass of the meter stick. Okay, so I walked you guys through that. You have the equation. Question 7 is simply figure out what this L is in meters. Okay, so given the data that I gave you guys, figure out what L is. Now, question 8 is calculate the sum of the torques and set them equal to 0. So we sort of did this on the video, but you want to re-show this. And then solve that equation for M, right? So this is where you solve the equation for M. And that's going to be the predicted mass of your meter stick in kilograms. And it should be pretty close to actually to the measured mass from the scale, right? So solve for M, see what we get. Hopefully it's pretty close to what we measured. So the other thing I did was I just simply weighed the scale. I massed the scale, or massed the scale. I massed the meter stick on the scale, and I got, it was 190.9 grams. So if you convert that to kilograms, it's 0.1909 kilograms. So this came from the scale itself. This is gonna come from your equation when you solve for M. You want to compare these two by computing the usual percent experimental error, right? So use the predicted one as like your accepted value. So when you do this error calculation, divide by the predicted one. Okay, then the last part of the lab is going to deal with a simulation again. So this is that same group, the PHET physics simulation group. You want to go to the simulation. It's the balancing act simulation. And then when you get there, and I'll show you this in a second, you want to check off several things in the right-hand little menu there where it says show mass labels, forces from objects, and level. And you also want to make sure the ruler is turned on. Okay, then what you're going to do on the left-hand side, here, actually, let me go to the simulation site to show you this. Okay, so balancing act is going to be the one that we want. You can either download it or just run it through your browser. We want to go to balance lab. So again, under show here, check all three of these and then make sure that the rulers is also turned on, okay? So what I want you to do at first is on the left-hand side, place a 15 kilogram brick at 1 meter. So 15 at 1 meter. And a 20 kilogram brick at 0.5 meters. So 20 at 0.5. And then use the second condition for equilibrium, rotational equilibrium, to calculate where a 20 kilogram brick should be placed on the right-hand side so that when you click this over, everything balances. So right now, obviously, right, there's much more weight on the left-hand side, so there's a much greater counterclockwise torque than there is for a clockwise torque. So this is just rotating and it's definitely not in rotational equilibrium. So what you want to do is you want to calculate using the sum of the torques equals 0 where you should place a 20 kilogram brick so that everything balances. Okay, so you want to show me that calculation, and then I would actually, move it to that location, wherever it may be, wherever you get, and make sure that you're correct. Make sure that it actually balances. All right. Next, what I want you to do is on the left-hand side, place a 5 kilogram brick at 1 meter. So let me move these back. So this is the next part. 5 kilogram brick at 1 meter and a 20 kilogram brick at 0.5 meters. And on the right-hand side, we're going to place the unknown package. So if you click over those other objects, you can put people on there if you want. But we're going to use this unknown package A, and we're going to place it at 0.75 meters on the right-hand side. And notice if I click on this, it balances, right? So given the fact that it balances, I want you guys to use the second condition for equilibrium, the fact that the sum of the torques equals 0, to figure out what the mass is of A. Like, how many kilograms is package A, right? It's unknown. You have to figure it out. Okay? And then the last part of the experiment is simply figure out these other masses. Actually, I think there's even more here. Yeah, just figure out B, C, and D, what their mass is in kilograms. And you don't have to do calculations for that. You can just play around with the simulation. You can put different masses on the left-hand side and then put the unknowns on the right-hand side. You're still going to have to do some calculations, right? You're going to have to use torques to figure it out. But the goal is just to figure out what those unknown masses are. And you can do that by playing around with different locations of different objects. Okay. One hint or one example is you could just place like a certain amount at 1 and then try and balance it at 1 on the other side, and by, you know, trying different packages. Like, that's one possibility of figuring out what those masses are. So however you guys want to do it, the goal is to figure out what all those unknown masses are. So B, C, and D. All right, so that's it for this part. Let me go back to the handout, make sure I didn't miss anything. Okay, so yeah, so again, question 9 was make sure you show me that calculation using the sum of the torques equals 0 to determine the moment arm for the 20 kilogram mass, such that when you place it there, it's completely balanced. And then you should check it. You should actually put it on there and make sure that it actually balances in the simulation, right? But this one, you're going to actually calculate, show me the calculation, like how you got that particular value. Then for question 10, right, remember this is where we put the unknown package A at 0.75, and we put some bricks on the other side at 2 locations at 5 kilograms at 1 meter and 20 kilograms at 0.5 meters. So again, using the sum of the torques equals 0, the second condition for equilibrium, you're going to use that to figure out what the mass is of A. So you want to show me that calculation as well. And in question 11, you're probably going to have to do some torque calculations, at least in your head. You might have to do this on paper. You don't have to show me them, but whatever method you want to use, right? If you want to just play around with the simulation, I want you to figure out what the mass is of package B, C, and D. Okay, that's it. So, and that was the last lab for the semester. So again, there will be some sort of lab exam for both classes, 207 and 206. I haven't figured out the details of that yet, but I'll let you guys know when we get closer to that. It's not going to be for a little while. All right, great, thanks.